CLI on a cross-platform IDE for C and C++. Download now.
Hey everyone, welcome to my talk on understanding the art of API design. First of all, who's this? I'm Chris. I've had the opportunity to build quite a lot of libraries over the years. And when working with younger engineers, I found that a lot of them seem to be making kind of the same mistakes along the way. And so I wanted to make this talk as a accumulated experience to give people a head start and give them an idea of what to look out for. Because it seems like people learn programming in university, they learn clean coding and code reviews, but when entrusted with their first architectures and APIs, it doesn't go that well for their first attempts. And then people tend to think, oh, this person can't be trusted to do an API. So other people take over whenever that happens, which, robs them of their opportunity to learn by experience. That's why this is so important to me, because a good API is not just a byproduct of functionality or some afterthought, but actively designed to help the user and not just some facade to functionality. So there's actually 4 key reasons why I think you carry a huge responsibility when building an API. First of all, your API shapes how user code can look, right? If we want code to be readable, then your API sort of sets the boundaries of how the user code can even look in the first place. Secondly, if there's a bug that you make when building your functionality, that's usually a trivial fix. One file change, you review it, and it's done. However, if there's an issue with your interfaces, then everyone's code needs to change, not just your own, but also everyone who's using your API. Thirdly, a bad API wastes a ton of people's time, not only in researching how it should look and how it should work and how it does what it does, but also, a bad API tends to lead people to make the same mistakes over and over again. Those bugs need to be found and fixed, and all of that is expensive because it costs a lot of time. And lastly, code is usually evaluated quite often. People, look at code in reviews, but architecture can sometimes hide a bit under the surface if people aren't looking out for it. So building the right API is very critical, because if you're not actively looking for it, it will spread across your projects, and then eventually you'll realize you have a huge problem rather than catching it very early, like you usually do with bad code. So as part of this talk, I want to have a look at what does a good API do, and then we're going to have a look at all those points and see how we can do them well. So first of all, a good API simplifies the mental model that you need to build your functionality. Secondly, a good API is easy to understand in terms of what can be done, right? What the API provides. Thirdly, well, it should be able to do the things that you actually need, right? Otherwise, the API isn't good to you. Then, obviously, it should be easy to understand how I can do that using the API. Next, it will encourage readable code for your users. Then, it should be hard to use incorrectly. And lastly, there shouldn't be any nasty surprises. So when you adopt an API for an entire project, and then after a month of using it, you will see that it causes any large troubles that you didn't see coming beforehand, and you regret transitioning to it. So let's look at the first point. A good API simplifies the mental model. So functionality is all the irreducible things your program needs to do in order to achieve its goals. And we're achieving a simplification of the mental model of this by doing 3 things to it. First of all, we're combining parts that belong together, and we're separating parts that don't. Secondly, we're hiding the complexity of the inner workings behind some, object with fixed boundaries. That's what we call abstraction. So the complexity should live inside the object, and it should be very clear from the outside object how to make use of that. Thirdly, and lastly, communication, right? In order to make the functionality do the things that actually needed to exist, those components will need to be able to communicate, but now in some transparent way rather than just modifying each other's values. An API now combines a collection of abstracted separated functionality that serves a combined but well-defined purpose. Actually, systems engineering can shape how those APIs will even be able to look. For example, if you use messages to communicate, then your only API is this message interaction, and the structure is very flat. This might be a good thing or a bad thing. I'm just saying that systems engineering has a very distinct impact on APIs. The architecture of your program now is built by layering APIs, by layering levels of abstraction from very, very large scale information to very specific to a particular topic. If one of your APIs now needs to talk to a lower level of API that isn't directly connected to it, it is breaking those abstraction layers. This is what we call spaghetti architecture. So those direct communication should be prohibited, and you should respect the abstraction levels, and you should build your API in a way that it's easy to make use of them properly. If you do now actually need access to a lower level of abstraction, it is better to get rid of the layer of abstraction in between, because now you're no longer relying on the functionality that it provides. And, your mental model isn't simplified anymore if you have to keep in mind what the mid-level of abstraction actually does. Obviously, and importantly, APIs aren't just separated horizontally, but also vertically. That means a certain level of abstraction might be using multiple different APIs underneath, and even though they're on the same level, they shouldn't be talking to another. So even though they're lower than you, they shouldn't be communicating directly. If the format parser needs to talk to the decimator, all communication goes through the model loader. So now, cool, we know abstraction, big fan. More better, right? Well, actually, no. It's kind of like a nice warm bath. If it's just right, everything's perfect. If it's a bit too warm or too cold, you'll know, but you'll be able to manage. And if it's way too hot or too cold, you should jump out immediately to reduce the amount of physical damage. And same thing happens with abstraction. So if there's too little architectural abstraction, then the mental model gets too complicated by just all the things to keep track of that are happening on your level of abstraction itself. Same for objects. If they contain a lot of state that is very complicated to keep track of, then they are very difficult to deal with, and your mental model gets polluted with all the things that are happening at a time. So you should usually separate them and introduce more levels of abstraction. On the other hand, if there's too much abstraction, then the actual functionality is actually spread between different layers. So it's very hard to keep track of, when you need to make a change, you need to touch multiple different places, and it becomes very complicated to keep track of the mental model that way. So you're not actually even getting rid of any complexity in the first place. So to simplify the mental model, we first ask ourselves, what is the purpose of our new or existing API? What does it abstract or separate? Secondly, we separate layers vertically and horizontally. Thirdly, we prohibit spaghetti calls, so calls that are breaking our levels of abstraction. And lastly, we're finding the right amount of separation and abstraction for our use case. Now, on to the next one. A good API should make easy to understand what can be done. Since we're talking about understanding here, there's actually a pretty good mental analog we already have, which is, APIs might be abstract mental concepts, but at the end of the day, they're just files and folders containing text. So comparable to chapter markers and contents of a book that we need to at least skim to figure out what it contains. So let's use this analog of natural language processing in our brains to get a bit better view of this. Is this text easily understandable? Well, it's in a foreign language, so it's pretty hard to say, right? But if I give myself the means to understand it on a level of comprehension, it will still be cumbersome to learn its meaning. But that doesn't just mean words. So if we use a different example, we take an old book from a bookshelf, and it will read, "And if some have compassion making a difference," well, usually, that kind of, I know what that means. Someone's being asked to be nice and make some positive change in the world or something. Making a difference means making a situation better. Everything's clear. Well, this piece of text was written in 1611, so making a difference actually had a different meaning back then. So we are reading things into this text that aren't actually intended by the original author or translator. So this doesn't like one-to-one translator programming, obviously, But we have similar things in C++. A struct and a class are functionally very similar in C++. However, they aren't used in the same way usually in C++ programs. A struct carries baggage from C, so we'd usually expect it to be POD. But a class carries more from the Java side. We're expecting member functions and potentially inheritance and stuff like that. The way struct is usually used when you modify a member of a struct, this is just the most normal interaction with a struct. However, if you modify a class in its natural habitat, that usually raises some questions. So first of all, why isn't that member private, and why isn't there some interface way to do this interaction rather than you manually modifying its members? We actually have more like this in C++, for example, pointers and references. They are functionally pretty much identical, but they're not used identically throughout our code bases. So the way we pick between them is usually shaped by our coding guidelines and policies of our companies and projects. So if we would say something like this in the wild, it would usually carry some questions. So why is this returning an int? Is this an error code? If it's the index, then why is it signed? What about the pointer of the item? Are they expecting us to, keep the object addressable because it's just adding the pointer, or maybe they'll copy or move the object from the pointer? But if we know that the cultural context of this company is that by policy, return codes are error codes and they're integers, and they never use references, they only use pointers, then it's a lot more clear what this does. So as you can see, like any other text, our APIs and interfaces have a defined target audience. This might be broad or narrow. This is not very easy to define sometimes, but the better you can define it, the easier it will be to make the right decisions for them. This is obviously usually not just struct versus class, but something like experts in a particular field versus the average developer versus newcomers to programming, or people who need fine-grained control over all the specifics, or people who just want to do the thing. Maybe it is modern C++ style or C++ style of a particular year, or C style C++. Or there's people who are very familiar with the STL and how the STL does things, and as opposed to people who don't. Fortunately, a lot of the cultural understanding we have as developers isn't just as developers or C++ developers, but also as humans. There's certain things that our human understanding just has inherently to it. For example, there's a maximum amount of things we can keep in our heads at a time, or we expect similar things to kind of live together and different things to be somewhere else. The tools we have at our disposal for making people understand what can be done with our API are the following. Folder and file structure. So even from that, people will be able to see kind of what our API will be able to do. And when they open up those files, they'll see namespaces, modules, if you're using them already, objects, enums, functions, then obviously the names of them, how they're positioned in the files and folders, how easy it is to find the stuff that people are most usually looking for, maybe comments on those things, very at least big picture, maybe separation comments between things that aren't necessarily as related as other things, but still belong in the same file. Obviously, templates and concepts, and maybe public type defs will be able to tell us this is supposed to work with other types or supposed to be used with templates. Maybe iteration, stuff like that. To make our objects easy to understand of what they do, they should have a focused scope, a single responsibility to the outside. Obviously, this is also really important from an architectural perspective because it reduces the mental clutter, but it also makes it possible to understand more easily what an object does if people are just skimming our API. So we want to limit the number of possibilities and directions that a unit can have. And if it would be hard to tell what it does, we should break it up into multiple parts. If you need some functionality, you can still move it to a different object. So for example, if we have a class file that might have exists and size and getting some properties, maybe reading and writing, and maybe you would want to be able to copy it, and then maybe you would want to analyze its read and write throughput, and why don't we need transactional file system interactions and be able to memory map it? And you can see like at some point there's a line here where this no longer should just belong to just this file, but would make much more sense in some other place to be able to understand more easily what the purpose of this file object actually is. So your objects should do one thing and do that well, and that should be reflected in the name. That being said, you should name things by what they do, not by what they are. You should be able to put that into one sentence and then derive a concise name from there. However, it is better for your names to be long and precise than short and generic or misleading. Consider the expectations that people are going to have from a thing with that name. What would they want it to do? And lastly, make your names mean something. If you can use multiple different words to express something, pick one of them and make it mean something, because sometimes you will need both of them, and then you can make one of them mean something and another thing mean another thing in your architecture, and it's very clear by just seeing the name and which part of the architecture you are. So to summarize, we want to make it easy to understand what can be done with our API by knowing our target audience and considering the understanding, by helping users via file and folder structure and the ordering within our files, by doing one thing and one thing well with our objects, and by making our names concise and precise by what a thing does, not what it is, and by making those terms in the names mean something across our architecture. Next up, a great API is one that actually provides what you need. This is actually tricky, so user feedback is going to be crucial here. So again, know your target audience. If you can, talk to them, understand what their problem is, and figure out what they actually need, which might be very different from what they tell you what they need. Consider all the required interactions with your functionality and don't just restrict it only to simplify your API. Don't do any narrow-minded use cases. If you provide an async method to do something, probably some person will need it to be synchronous. And if you require a callback, maybe some people might appreciate the opposite. But there isn't very much I can tell you here. Mostly just talk to your users and figure out what they need. Cool. Now we know what your API does, and it does what we actually want. So it should now be easy to understand how we can do that using your API. To make that easy, there's actually two parts to this. First of all, we want to allow people to carry themselves by their intuition and cultural context so that they don't need to even learn anything for our API. And secondly, when they do need to learn something, we need to respect that learned knowledge and make use of it again and again. So, how do we let people be carried by their cultural understanding? Well, we do this firstly by intentionally using language constructs and the understanding that people have of them. A struct, for example, people would usually expect to be POD, or at least trivially copyable. So in this case, just contains some enum and 2 integers. It might also be used as a tag type, or potentially for template specializations. That's where you commonly see structs being used. A class, however, usually encapsulates lifetime. Commonly, classes also have custom copy and move semantics, so people will usually take that into consideration. Also, classes usually inherit from other classes. Certain functions might be overwritten or just virtual. Maybe the classes are just all virtual and none of the functions actually exist. Stuff like that. Enums, for example, are phenomenal for communicating state with fixed possibilities. So basically all states. They're usually clearer, even if there's just 2 different options where you could use a bool. An enum is usually more readable, especially to reviewers. For example, in this case, in the lower one, we wouldn't actually know that the second parameter is the append mode if we were reviewing this code. But when we see it explicitly specified, this makes it so much more clear. Enums are also incredible for return values. So if you want to represent a state that happened that isn't a type, they are incredibly good at communicating this clearly. Now, let's look at cases where you see an object and ask yourself, well, how do I get an instance of those? A public constructor tells you you can make one of those objects. Static creation functions tells you can at least get one of those, and make something function provides some other way to make it. When it comes to functions, static member functions generally just have to do with the object, but not with instances of it. Const member functions are more of a show me, tell me something, where a non-const member function is a please change the object into this. And free-floating functions are usually pure, or at least somewhat separate from the objects, or sometimes they're just used for utility. Const references for parameters are usually just a let me have a look at this during the duration of the call. If they're being returned, it's like this might be made of glass, please be careful. where const pointer usually means let me look at this across my lifetime, so for the entire duration of the object. Non-const references are more of a let me poke at this temporarily during the duration of my call. If they're returned, they're also made of glass, so you should be careful when you change them. Whereas a pointer is more of a let me poke at this indefinitely or during my entire lifetime. An R-value reference is a this is yours now or this is mine now. And a pointer is please let me look at your intestines, or if you're returning them, don't return them. So we can also carry people at their cultural understanding by using common patterns. For example, when you take standard span or standard vector, or maybe just a pointer account, that is a pattern that people are usually familiar with for taking lists of things. Or if you provide begin and end, people know that this means iteration. Or standard optional, variant, and expected communicate which of a possibility of options happened. Standard unique pointer and shared pointer communicate ownership. And by picking wisely between size, count, bytes, and capacity, we make it easy for people to understand which one of them they're actually getting. And the second part to make it easy for people to understand how our API can be used is to respect their learned knowledge, which means consistency. Consistency in naming. So a certain term should mean something across our architecture and should tell us where we are, even if that term can be used interchangeably in natural language. Consistency in approach. So, for example, if we have this concept that objects member functions return references to the object themselves when they're configured, we shouldn't just be using that for one object, we should be using that consistently or not at all. Or if we have the concept of sinks and sources, and we have the ability for one of them to push into the other one, we shouldn't just be using that for two fringe objects, but for everything it would possibly apply to. Consistency in behavior. So, for example, when we're confronted with an illegal input, are we trying to guess what the user actually wanted, or are we just exploiting their face to tell them this is not how to use this API? That should be consistent across your entire API and preferably architecture. And consistency in types. So if you're using a type as a return value, you should also be able to take that as a parameter again and so forth. And that should be possible across your entire architecture, preferably, to at least allow people to stay in your system if you're already defining it. So to summarize how to make it easy for people to understand how to use your API, use their pre-existing knowledge in your favor. And be consistent in naming, approach, behavior, and types. Make people learn something once and allow them to stay in your system if they're already using it. I have two little extra points here. First, provide reasonable defaults, especially with template types or if types require extensive configuration. Give people some reasonable starting point to start from. And secondly, provide documentation when people need it. They might not always need it, but when they need it, they should be able to find it. Next up, a good API should encourage readable code. The resulting code from using your API should be readable and reviewable very easily, irrespective of the complexity of the interaction. Generally, simpler is just plain better, but be cautious. This doesn't just apply to your code. It applies to all the code that is affected by your API. So your implementation interface, but also all usages of your API. So don't just make things simple if the user has done something special to their object, unless the gains are incredible and the interaction is very common. And if you do that, communicate it very, very well. And provide great feedback for the people who are using it incorrectly. So concepts, asserts, and so forth. Similar story with inversion of control and callbacks. They might be able to reduce the complexity temporarily, but if they're used in bulk, they will destroy any sense of separation and abstraction throughout your architecture. This doesn't just mean lambdas and function pointers, but also objects passing themselves to other objects that then modify them or call some function on them or something like that. Now, there is a common pitfall here when people try to build something simple, which is just considering the 95% of simple cases. But some interactions are just inherently complex, and you need to acknowledge them. So simple interactions should be trivial, but complex interactions that are valid should still be possible. It's acceptable if your highly configurable multi-stage conversion pipeline setup isn't just one line, and it shouldn't even be. But that doesn't mean that the most basic interaction with your API that is possible would require two different command queues and target buffers and inherited handles, factories, and advanced thread queue setups. It should just be simple. That doesn't mean that the simple use cases are invalid. They are very important. If they're handling 95% of the cases, that is the most important cases to handle. But, you can't leave out the cases that are enormously difficult, and they can't be incredibly reliant on implementation details in order to even work at all. I usually like to call this the complexity slope. So the simpler the task, the simpler the API should make its implementation, and the more complicated the task, the more okay it is for that interaction to be more complicated within reason. And the floor of that complexity slope should still be reasonable, so that trivial interactions don't require deployment. And the slope itself should also be reasonable, so that it's not impossible to do something complicated. Now, that's a great requirement, but how do we actually build an API that looks like this? Well, to put it simple, by attempting to do that, right? By trying to consider how it would look like to use it before we build the API. And the way we do that is simple, pseudocode. Simple as that. Your API doesn't exist yet, but pseudocode can give you any magical interface you could ever dream of. So try an approach, see where it leads you, and don't expect your first attempt to be perfect. That will come with time. If you can't simply make it beautiful after a couple of modifications, just try a different approach and see what that does. Consider all the simple and complex common interactions one would do with your API and quickly prototype them. This is actually where test-driven development can score you some bonus points in terms of API building. But firstly, you can do the same thing with just a bit of pseudocode. And secondly, we don't necessarily want to optimize the readability of our test code, but the readability of production code. Now, you've found some magical new API that works beautifully and does everything you want to do. Stick to it. The number of times I've seen people come up with a nice solution and then disregard it because it was complex to implement with their existing code is astonishing. The whole point is to ignore the existing code. The whole point is to ignore everything except the hard requirements, the thing that actually need to be passed as parameters or you need access to or something like that. It is not to make it simple to implement. The simplicity will be of the entire system, so of all the code. So if the resulting code inside your API actually turns out more complicated and ugly, that might be worth it because you're not considering just your API itself, but everyone using it. And if you're making everyone else's code a lot more simple, then that is worth having a more complicated API internals. However, obviously, if you're over-engineering everything for 2% more gains, that is not worth it. Complex APIs with clean code behind it are much worse than some heavily optimized hand-and-rolled assembly behind a beautiful, simple API. You can easily change the code, but you can't easily change the API. Now, if you have an approach that works, you don't need to get the names perfect on your first attempt. You can take your time picking them afterwards when you're happy with the approach. The code using your API should be simple to implement, simple to read, and simple to review. We shouldn't require people to understand how implementation works or any other internal details, and they should need to read as little documentation as humanly possible. Otherwise, you're wasting a ton of people's time when they're trying to learn the API and review code using it. The approach people commonly use without any prior thought is one that I call bottom-up. It's great for building functionality, but it doesn't lend itself well particularly to APIs, because they're more of the afterthought of the scenario. So the way it works is, for example, when building some sort of neural network, they would first build the implementation details of the neurons and activation functions, then build the interfaces for them, then build some sort of layers on top of that that are making use of both. Then they realize, we actually need some way to, hold the buffers in place to we're able to reuse the buffers for it. So we'll build some sort of training engine on top of that. And then eventually we build our neural network type, if we're lucky, on top of that. And then the users can use that. The problem is that it makes the functionality shape the APIs, and we don't want the API to be an afterthought. So this is basically the worst case for our neural network that will actually be used by the end user to have a nice API. The approach I usually recommend to people is what I call top-down. The way that works is you first build your fake user code using pseudocode. Then you build your neural network interface from that. Then you realize, I will need some sort of, training execution that will hold things in place over time. So you build your training engine, and then below that, I need actual layers. So you build the actual layer API. And then at the bottom, you actually start implementing your neurons and activation functions. The trouble this sometimes runs into is that people don't know yet what their hard requirements are. So when they actually then build the neurons and activation functions, or maybe even the layers or the training engine, they'll notice, oh, I actually need access to this parameter, or I need this configuration somewhere, and they'll just add a parameter here and there. And that will start polluting the interface, so you don't actually get the interface they initially designed, but rather the interface that is the fifth or sixth iteration on top of that, which I don't mean in a good way of iteration, but rather it already accumulates legacy problems during their first iteration. The way to build around that is an approach that I usually call bottom top down. So in that approach, you first build your neurons and activation functions so you actually will know what the hard requirements are. Then on top of everything, you build your fake user code. So you prototype the API of the actual neural network. Using that, you build the actual neural network. Then realizing what you need underneath, you'll build some sort of training engine again, and then the layers. And so you had the opportunity to build most of the interfaces top to bottom, which tends to produce very nice interfaces, but you made sure that you already know all the requirements that you have. So you don't need to iterate upon your interface as often because you already are much more aware of the hard requirements. And then obviously at the end, you replace your fake user code with actual real user code. However, even with all that in place, it's sometimes very hard to know what the lowest level even is or what that would do. So if that's the case, I usually recommend people to just do a cross-section of their API. To start with one interaction that they want to be able to execute at the end of the day, and then just imagine for that interaction what the interface would look like. So the highest level, or the user code, talks to the highest level of our API, which talks to some lower level abstraction and so forth. And then after you've completed this for one interaction with your API, you basically trial the next one, and so forth. And some of the interactions you initially planned won't work out the way you initially intended, but you'll get a much better picture of what you'll actually require to do. And then when you have a good understanding of what your different layers will need to be, you can then start implementing your lowest level. Awesome. Now we've built a great, simple to use API over potentially an entire subsystem. What now? Well, there is a common death that even good APIs fall to, which is time. Your API might be amazing when it starts off, but over time, people might need to make some slight alterations to it because they need some configuration parameter here or there, or need some other option here or there. And, number of parameters on function grows and grows and grows. And after some time, it has turned to some monstrosity that you never intended it to be. Usually it's just a rewrite then, or you need to have some legacy support and build a new API on the same backend or something like that. So if you make additions to an API or even slight changes, always consider long-term consequences. Sometimes there will just be a cutoff point at which it's better to add a new abstraction layer maybe that will provide this functionality, or maybe the functionality will have to resort to a lower level of abstraction, or one that you'll introduce in between. So be careful when reviewing code that makes changes to an API, because it might over time become a bad API, even though it started out as a good one. So to summarize, we encourage readable code by our API by trying to make the entire system simpler, not just our API. Simple things should still be trivial to perform, and complex things, if they're valid, should still be possible. We do this by using pseudocode and prototyping APIs and designing them top-down, or potentially bottom-top-down if necessary. And we evaluate interfaces when making changes to make sure that our change doesn't turn a good API into a worse one. Awesome. Next up, a good API should be hard to use incorrectly. This might not sound the most relevant at first, but is absolutely crucial. If you've ever had the pleasure to build an API that's being used by a lot of people, you know why. You've seen the code of people using your API. And if there's some interaction that isn't clear or that actually suggests the opposite of what you intended, there will be a ton of bugs and issues or workarounds for things that you didn't intend. And those repeated bugs waste a ton of people's time, which absolutely isn't necessary. Well, how do we do this? If there's unexpected behavior in your applications, and there probably is, can we remove it? Which doesn't necessarily mean can we remove the functionality itself, but can we make it not unexpected anymore? Potentially this is just done by moving it to a different place or something like that. But if that isn't possible, there's a bunch of levels of escalation. So first of all, obviously, you can put a comment on this, but this usually doesn't suffice. Don't expect people to just read some random comment. This might suffice if there's like a, complexity of the underlying code that you want to warn people about or something, but it isn't going to, stop people from doing something stupid. Next up, parameter names. People will see them when typing your code usually, so they will make clear what this thing is. But, they might not suffice and people might not be reading parameter names or just copy pasting code and assume what the parameter is. Next up, you can use function or inner value names because people will actually need to type them and see them. So that's the next level of escalation. You will be able to make a lot of things a lot clearer already here. But that might also not suffice. If you really need to make people think, it's usually easiest with a type, with an explicit constructor or some static construction function that clarifies a certain interaction. This will usually be the worst you will need to do in order to make people think, why is this a certain way? Why is this integer wrapped by a type? Why can't I just pass it a certain integer? There's still one more level of escalation, which is basically making people type out that what they're doing is dangerous. This is sometimes necessary for breaking levels of abstraction, if that is somehow necessary for some operation that someone needs to do, and you do actually have no easier way to do this. Make people type it out. But I would usually, at that point, there's probably some easier way usually to achieve that. That being said, encourage proper use of abstraction layers in your APIs. That will remove so many bugs from happening. Make internal helpers inaccessible. They're not intended for other people, and you don't want them to use them. They're intended for you to have some implementation details behind them. If you intended other people to do that, then add that to your public API through some way. But making use of internal helpers is a very bad idea. So make them as inaccessible or as cumbersome to use or as obviously internal as you possibly can. And lastly, check the validity of parameter values and configuration options. Make people catch early that it's their fault that something doesn't work rather than, your API failing deep inside. And then the user might actually think it's your fault rather than theirs, and it will be hard to track down and will waste their time and your time rather than just telling them straight up, this configuration parameter is invalid. Cool. Lastly, no nasty surprises. We've talked about it. When people have adopted your API, don't make them regret it. Some of this stuff is systems engineering level things, but if they're unclear, you should still, clarify them to make sure everyone's using them consistently. So know how error handling works inside your API and inside your architecture. Know how memory allocation works and memory allocation failure works inside your API. Handle and detect edge cases properly. So if you're taking const char pointer, consider that this might be a UTF-8 string. Don't excessively limit what users can do after they've transitioned to your API. If there's a reason why people would want to do something that is valid, let them do it. That's especially important if your users can't modify the source or they don't have a clear communication channel. Don't make false promises. So for example, iteration doesn't just mean that a singular user can iterate at a time, but people can create multiple iterators that work in tandem. So only use iteration when you actually provide all that functionality. Your layers of abstraction should be compatible and consistent. If a user needs to transition to a lower one, they shouldn't need to suddenly start using very different types to do the same kind of thing. And another shout out to overuse of inversion of control. It is so good at breaking all resemblance of separation in an instant that I can't warn people enough of it. At least to overuse it. When it comes to these kinds of things, learn from the mistakes of others. You don't need to make them yourself. Make a mental map of all the issues you come up with that are nasty surprises, and when you're in a position to build something comparable, solve them as part of your initial design process. Okay, cool. That's all the parts there are to a good API. It simplifies the mental model. It makes it easy to understand what can be done. It provides the functionality that you need. It's easy to understand how to do it. It encourages readable code. It is hard to use incorrectly, and there are no regrets and no nasty surprises. Now, you probably have a lot of pre-existing code. We've discussed strategies about how to refactor it and how to build new code and new APIs, but how do we determine whether our existing APIs qualify as a good one or as a bad one? Well, there's 3 pieces of evidence we can investigate. First of all, your architecture and the corresponding mental model. Secondly, your APIs and their interfaces themselves. And lastly, how your APIs are being used, so the client code. Let's first look at ways you can determine the quality of your API from the mental model and architectural perspective. So, do you know where your abstraction layers start and end? If not, stop and clarify. Well, what's the purpose of them? If you can't easily name or explain the purpose of every single layer of abstraction in one sentence, then you probably have too many of them, or badly chosen ones. Is it hard to keep track of the flow of dependencies? So when you just look at the files or the class names, is it hard to tell where they belong to your architecture? You can address this by doing consistent naming, and you probably have too much separation. So for example, for storage, buffer, and data, they all kind of mean the same thing. But if we pick them wisely in our architecture, so for our image pipeline, for example, we take buffer to always be associated with files and input-output, and data to always be associated with images, which might not necessarily be the best choice, but just to illustrate the idea. Then if we see the word data or buffer, even though they're very similar words, we always know where they belong into your architecture. Are there many similar things inside your architecture? And it's also hard to keep track what each of them actually does and how it interacts with the others. Then you probably also have too much separation, and you might just be able to collapse a bunch of levels of abstraction into a singular one or into 2 ones. Do you have objects with complex internal state that's hard to keep track of? Usually that happens when a lot of APIs come together on one layer. Usually I would recommend then splitting them up into multiple in-between levels of abstraction that deal with corresponding parts of the API, and then only dealing with those in-between layers of abstraction, your actual implementation, to, keep the mental model simpler. That especially works quite well when, the certain values of a state change together all the time, so you can make use of lifetimes to encapsulate that. Or there's numerous functions that operate on the same part, where you allocate an image, you update an image, you destroy the image, and you're why isn't this just an image? Then allocating the image is the constructor, destroying the image is the destructor. So I've communicated that without any additional meaning, just by context. And then I only need an update function to it, which is very simple. And that, doesn't need to be the image function for your entire library, but might just be some internal helper type. Next up, we can evaluate your APIs by looking at your API code. So when we look at that code, first of all, we should ask ourselves, who's your target audience, right? In this example here, the top line is probably targeted more towards people who are familiar with the SDL than the other one. Or maybe your target audience needs extensive configuration and needs access to all the different options to do something, as opposed to, maybe they just want to play some sound and they're just happy having just a singular function call with no configuration options in sight. Then when you open up your project and we just look at your directory structure, how easy is it to find the functionality that people are actually looking for and the corresponding documentation? So for example, if we have very generic folder names and file names, it might be very hard to find something very specific that people are looking for if they're not named by categories. Whereas if we name our folders nicely onto like subcategories that might be relevant for people and our file names very distinct to what they do, people have a much easier time finding where to start with your API. Then when we open up those headers, how easy are they to navigate? How easy is it to find the components you're actually looking for, right? Is this just huge file with tons of implementation in there and, it's hard to even keep track of where an object starts and ends? Or is this very well documented and like nicely built for people to have a look and like targeted towards the people who will be using that API? Then are things named by what they are rather than by what they do? So a backend holder base doesn't tell me anything about what it actually does, apart from holding a backend. But then what does that mean? Where this might actually just be a notification recipient or something. Would the use of common language constructs simplify your API? So taking const char pointer into ints doesn't tell anyone what this is, but if we make that a string view and a priority enum, this is suddenly much more clear, right? Does your API have consistency in behavior, types, and naming? So for example, when you return file data from read file, when I write file, can I also pass that file data? Or maybe you have a lot of different helper objects that kind of do the same thing as other helper objects. Maybe you can unify them so they're consistent across your architecture. And lastly, let's evaluate the code of people using your API. So this might be company internal code, or maybe even your own code if you're using some other level of abstraction, or it might be external code. So does any of it circumvent API boundaries or object boundaries or rely on implementation details? So for example, here we're like getting the decoder object from inside the playback engine to just push it some random bytes to do something. Maybe we should support that behavior and add some skip frame option if that's what they wanted to do. Maybe it suffices to just rework your code and all the functionality already exists. Or maybe you need to transition to a lower level of abstraction anyways because you need access to those lower levels for some functionality inherently, and don't want to make that available as part of your higher level API. So you basically have no other option if you don't want to rely on the implementation details of that like mid-level of abstraction. Does the client code jump through unexpected hoops when making use of your API that you didn't see coming? Then probably you can make that interaction simpler or even possible if it wasn't without, weird acrobatics. So in this example here, the user is seemingly just trying to turn their YUV image into a black and white version, but they currently need to do that by turning every single pixel into a monochrome version. Maybe you could just, if you already have a black and white image, we can allow you to blit from the YUV version, or we can have a function on images that allows conversion, and monochrome is just one of the conversion options, something like that. If you look at usage of similar functionality, maybe even of competing APIs, do people commonly do something that you don't provide? So do they suddenly start using some random other functionality to achieve their goals? Then maybe you should support that. So here, apparently, we don't support setting the volume to play a sound. And if we look at some competing API, they apparently take that in their constructor alongside some other configuration parameters. Maybe we could adjust our API to take the volume as part of a parameter for play that defaults to full volume. Or when looking over those use cases, just consider what would be the optimal API for just this specific single case, and then just collect them and see maybe there's some common patterns in there and there's functionality that people commonly would like to have. So you can introduce some helpers for those use cases, or even add some new level of abstraction to do that for them. But obviously you shouldn't pollute your API randomly. So in this example here, people are just like trying to get some gradient. So potentially we could add some static member function to image that just initializes it to a gradient if that's a very common functionality. And lastly, are there any common issues you stumble upon or even bugs? So for example here, apparently our image size is the total pixel count rather than size in bytes, but data retrieves the raw data. as a standard byte. So when pixels aren't actually 1 byte in size, people don't realize that and start writing less than a total image size. So the proper way people should use is too unintuitive. So how can we change your API to make it more cumbersome to do this incorrectly and make people think I'm actually doing this right, or stop them right in their tracks before they even think about doing it this way? So to summarize this entire talk, building good APIs consistently requires active design. It doesn't just happen on a whim. Know what your target audience is and what they're looking for. Otherwise, you won't be able to build an API for them. Ask yourself, how does your object or API simplify the mental model? Design systems top to bottom by using pseudocode, not as a byproduct from implementation details. Name things by what they do, not by what they are, what they represent to the user. Encourage simple and readable client code. You doing the complex part is the whole point. Consistency is important in names, approach, types, and behavior. And lastly, eliminate unexpected behavior. Eliminate the unexpectedness of it. Awesome. That was my talk. Thank you very much for listening. I will see you in the Gather Town in a second. Take care. Bye.